All right. I heard that I'm on the mic. There you go. Where's my presentation? Let's stop here. Perfect. All right. That's nice. I see there's actually quite a few people that either already have food or just seem to skip food, so probably on a diet or something. It's really good to be back at Devoxx. I think it's been 6 years for me, so I really enjoy being back. Before we start, and don't let your food fall just by raising a hand, right? Don't use the other one. Who's using Postgres? Oh, that's good. Who's using Java in Postgres? That's good. We're not talking about Java today, I'm sorry. I know it's Devoxx, but we're talking about Postgres. Time series? Somebody's using time series? Okay, so who knows about what the time series is? Okay, see, some hands are not up, so it's good. We're starting a little bit slow. But first of all, this is me, and I used to work for Timescale, and that is when I submitted this talk. I still think that Timescale DB is an incredible piece of technology. So don't get me wrong, I'm not working there anymore, but I'm happy to talk about it still. I've been with a couple of other companies in the past. Some people may know me from my time at Hazelcast, which is quite a few years back. I've been at Instana before it was acquired by IBM. There was some weird thing that made me leave, and it was obviously not IBM. I had my own startup before I joined Timescale. And what I normally do is, I know it sounds cool, developer relations. I travel the world, I tell people about technology, and cool technology. It's not all about partying, but it's a big part of it. I'm coming from a strong engineering background, but that is not super important. So what is a time series? And is there anyone who wants to try and give like a one-sentence explanation of a time series? No? All right, fair enough. So when we talk about time series data, there's a couple of things which are kind of obvious, right? So time series always has something to do with time. I mean, the name says it. So any kind of financial transaction is a pretty obvious example. If you transfer money from your bank account, it better is booked into the account first before you try to put it somewhere else, right? The same goes for stock prices. Stock prices only make sense if you look at the stock price for a specific symbol over the course of a certain time. Can somebody guess what that is? Just scream it. I give you, I heard it already. I just wanted to say, I give you a hint. It's a cryptocurrency, and I heard it Bitcoin. Yes, that was the Bitcoin course, I think in September 2022 or something. I hope nobody invested in that, or at least got some money out of at least. Anything IoT, and I said I had my own startup. We did some hardware and software system. It actually we hang that system into an animal barn, and it was measuring things like temperature, humidity, ammonia levels, all the kind of stuff that has influence on animals, and we try to make the animal welfare better, but that means what we actually looked at was the change of a certain measurement over time. So time series. Observability, anyone using observability tools? All right. Anyone using Instana? All right. Still? All right. At least one Instana person. Whew. I did my job. That is also Instana, but it's a different thing. So everyone knows things like CPU metrics or like CPU usage, memory usage. Instana actually went a step ahead and said, hey, if we have all the metrics and the traceability information, we can give you a graph of what your infrastructure looks like. Fully automatic, right? It figured all of that out. But all of that still built on different time series information, many different time series being correlated into each other. And my favorite, favorite example from a usability perspective or from a usage perspective, that is from a Netflix presentation. It's on YouTube, and I always forget to add the link. But just search for user analytics on Netflix, you're going to find it. Netflix has a big belief in data analytics, usage analytics, for obvious reasons, right? Because their only use case, their only reason to exist is to make us watch more. So the whole rating system, the whole recommendation system, everything, like every single decision what to produce next is basically built on that. And the presentation is incredible. They go very, very in depth how they actually do that, how they take the data, and how they analyze it. A really interesting talk. But the best and my favorite from a joke perspective is the Marvel timeline. That is every single Marvel movie in a time series. And to be honest, I'm not a big Marvel fan. I'm not a DC fan either, so I can say that without being stoned to death. I did not know how many Marvel movies there are. It's nuts. I mean, look at that. What is it, like 145 or something? Something like that. Brilliant. It's probably Spider-Man 1 like 15 times, but hey, is Spider-Man Marvel? Did I embarrass myself? Oh, okay, see people nodding. Ooh, no embarrassment. All right, so the one-sentence explanation, a time series is a time-related observation or a set of observations of a specific subject. So we look at something over, some change of something over the course of time. For stocks, it would be something like, hey, you obviously need some timestamp. You need a price, which is the metric we're looking at, and you have some meta information, like in this case, the symbol name, which could be IBM or whatever. For an IoT metric, you may have a slightly different version of metadata, like a device ID, maybe a location ID. You have the actual sensor value, whatever is read, and you still have a timestamp. So the important thing is the timestamp. And it goes actually further because oftentimes people would consider or would not consider something like invoices a time series. I think it is because I can only refund an invoice if it was actually created. So there is some time relation in that. It's not in the like millions or billions of rows of like data, but I don't think that it has to be. To give it all a little bit of a perspective, that's the New York Stock Exchange. And they have 4.2 billion transactions a day, which is a good number. Who has 4.2 billion transactions a day? OK, nobody from CERN here. That's good. I asked the same question at CERN, and there was quite a few hands up. That was disturbing. But that means that per second, that is like 160,000 operations, or 160,000 transactions, right? The really bad thing comes in, by law, the New York Stock Exchange is required to keep all of this information for like 5 years, which adds up to like 5.4 trillion transactions in the database. I think they may have some magic with different databases, some more cold storage, but I know that at least everything up to like the last 2 years needs to be readily available. So if you go to a website and you say, I want to see that stock symbol, up to like 2 years, they have to show it immediately. After that, they probably have a little bit more time. So why would you do all of that in Postgres anyways? Who thinks Postgres and time series is a great combination? OK, 1, 2. What does the rest of the people use? Influx? All right, some Influx users. QuestDB? All right. Just scream it at me.
Cassandra.
All right. Fair. Nobody's perfect. No, Cassandra is a good database. I'm not sure if it's a good fit for time series. I expected somebody to scream Mongo time series or Redis. Cassandra was a first for me. All right, anyway, so why would you do that in Postgres? I think the answer is simple, right? Postgres rocks. Who disagrees with that? Who disagrees? Whew. Don't scare me. I'm making specific questions. You have to listen. There's like very specific nuances to the questions. All right, so Postgres rocks, and I'm glad every hand went down again. That's good, because I really think Postgres rocks. Changed my mind, but you don't have to, right? But there is a few reasons that are actually more meaningful. Obviously, it has a very established ecosystem. I think that is obvious, right? It's around for ages. I don't know how many decades now, maybe 2.5 or something. It's rock solid. It's production proven. People know that it just works. From my perspective, one of the big differences to a lot of the other open source databases, it has a rock solid storage engine. We know we can recover from basically every fault. It's really hard to crash a Postgres instance in a way that you can't recover. Don't throw away the replication logs. That's a bad thing. Been there, done that. But the other thing is it uses SQL. So who knows at least some SQL, right? Who knows SQL a little bit more? Who uses it day to day? Who knows Flux? There must be at least 2 or 3 people. OK, fair enough, because I heard influx a few times. Who knows PromQL, if that is still a thing? There you go. But the amount of hands is vastly different, right? Everyone knows at least some SQL. And that's important when you want to analyze data, when you want to look at data. The other thing, and I'm not saying do this in production, please. Don't get me wrong. I consider Postgres a multi-model database. Multi-model in the sense of there is an extension for graph databases. There is an extension for key value stores. There is JSON and XML documents built into the database. There is a time series extension for Postgres. Guess what it is, right? It's not timescale. But there's a little bit of everything. And in theory, at least, and I tried it, and it was fun, you can put all of that in the same database and make a massive SQL query joining over, I don't know, 5 or 6 different data models. That was insane. It was nuts, and it was fun. As I said, don't do this in production, but just knowing you have the option to just spin up another Postgres and say, hey, I can stay in the same technology is a big plus from my perspective. As I said, and you can join between all of this. And obviously, like Duke, the mascot is perfect. Elephants are great animals. They have a lot of knowledge and a lot of memory. Obviously, that is exactly what you want for your database. So how would you do this in Postgres? And now it's where it's getting a little bit more hairy, let's say it that way. And I actually fixed it. Normally, it said sharing instead of sharding. It was always supposed to be sharding. I was just scared that I didn't fix it. So who knows what partitioning is? All right, that's good. Who gets tears in your eyes when you hear the word sharding? All right, all right. Luckily enough, today, sharding is used in a slightly different way, but at least a couple of years ago, like a decade ago or so, when you ask somebody who works with databases about sharding, it was always like this weird number range kind of thing with different database instances. Don't ever ask me how it works. It magically happens, right? And Timescale came up with the term chunking, which kind of is interchangeably usable with partitioning. So consider we have a 10 terabyte table that is a good size. It's not massive. It's not small, right? 10 terabytes is pretty good. So with partitioning, you would go down and say, OK, let's split that apart into something like, in this case, 2.5 terabyte tables. I still think 2.5 is not exactly what you want, right? You want to make sure that stuff fits into memory at some point. So what you would end up with is something like more in the 1 to maybe 10, 20 gigabyte partition size. So every table that is part of the overall data set is something 1 to maybe 20 gigs. And that means, remember, 10 terabyte, that is a lot of tables. I'm not good in math, but I know that's a lot of tables. Why you do those things is, not why, how you do those things, there's 3 options. There's ranges, and ranges is exactly where sharding comes in, right? You have number ranges. Can be good, can be bad. For time series, surprisingly, I guess, number ranges work extremely well, because what is a time range? It's a number range. Do you want to do this for anything else? Probably not. Please don't use customer IDs or anything like that as a number range. That's a really bad idea if you have 20 customers which are super small, and you have one which is very large, you don't want to have them in the same in the same number range. The second alternative is a list partitioning, and those are like the Postgres options, right? List partitioning gives you the option to say specifically, I want this ID and this ID and this ID in that partition, and those 100 other IDs in the other partition. When you remember big customer, that is probably what you want, right? You want to make sure that the big customers have like a massive instance, and you may or may not share infrastructure. And for smaller customers, yeah, I mean, they're small. They're probably not as much worth, if that is a term you want to attach to a customer. They can suffer. Who cares? Especially, you might have seen that. I've worked for Ubisoft in the past. A lot of the online gaming industry works exactly that way. There is a few big, massive customers. They actually call whale, which is interesting. That means they paid a lot of money already to the game, and there's a good chance they're going to pay more in the future. And you want to make sure that this person is very happy. I don't know why it seems to be very unintuitive, right? Making like your big paying customers happy. But that is how it works. And the last one is hash partitioning. And hash partitioning is exactly what it means, or what it sounds like. You take some key, you create a checksum of it. You have a number of partitions. You take the checksum, modulo operator, number of partitions, and something comes out of it, right? 10 modulo 2 is 5, something like that. Was that actually correct? I think it is. And why you want to do those things is for 4 very specific reasons. First of all, if you end up in a sequential scan is known. So the worst situation that a database can have, where you literally walk through every single record one by one just to figure out it doesn't match your query, which is normally what it is. If you end up in those things, because of the tables being very small, it's much faster. But the bigger thing is indexing is much faster, because normally, especially with B-tree indexes, you would have to update a lot of the index. Because the partitions are smaller, the indexes are smaller, and you don't always have to update the whole index. You only update a part of the overall index, basically the small thing for the partition. And then there's partition pruning, which says, stay with the time series example. I'm having data for the last 5 years, but I'm only asking for like January 1st, 2023 to today. That means I can remove every single partition from the query that does not contain any of those data. And then you have partition detach, which is a really interesting concept in the implementation that Postgres has. You can actually detach partitions from one table and attach it to another one. The idea behind that, I never fully understood why you would actually do that. The only meaningful thing that I can imagine is you have multiple table spaces on different disks, like NVMe and spinning disk, and you say, OK, now this partition only keeps data for like, I don't know, older than 2 months. I want to move that actually from the NVMe drive to the spinning disk, right? Making it slow or cold memory, something like that. There's other ways to do that. I think that it was the idea behind detaching and attaching. But it feels weird to detach something from one table and attach it to something else, especially when you get into the situation where you have to update the table afterwards. So you add a column or something. You always have to make sure those are like 100% identical. So let's do some demo. And demos are always nice. What I want to do is tell you a little bit how you would actually do those things in Postgres, right? There is a couple of ways. There's an old way, there is a newish way, and there is timescale. Let's see if we have time for timescale. It's always like a hit and miss. So what we have is I first generated some helper function, which is random between. It just gives me a number of a specific range, 10 to 50, something random. So let's make sure that the table does not exist, and I think it doesn't. Yep, all right. So let's create the table, and it works. There we go. Here's our table. And we insert something into it, which does not work. Where's my random? I'm 100% sure I had that. But let's recreate it. There we go. Magic function. Probably moved it out of public. There we go. OK, so 786,000 something rows in 2 seconds. That's good. And we can say, obviously, we have like 3 months of data. And you see this talk is actually a little bit older. So we created data between the 1st of June 2022 and the 31st of August 2022. So 3 months of data with an interval of 10 seconds. So every 10 seconds, there's a random value. If we want to read that, and let's do this on the console because it's a little bit easier to see. If I do that, we end up in a parallel sequential scan. You remember I said sequential scan is the worst thing that can happen? The parallel sequential scan is just so slightly better. That means that Postgres at least decided, hey, I can look at different things at the same time, right? But we didn't have any partitioning yet. And worst of all, we don't have an index. So let's do the same thing. And when we do that, now that the index is created, the query is much simpler because now we have the index condition. And it's also much faster, right? Because now the query planner can actually look at the index and say, oh, most of the rows don't matter to me. So I only have to look at whatever is around, right? So you have 42 milliseconds to 4.7 milliseconds. All right. So that is the no partitioning at all version. That is what a lot of people have when they start out with Postgres. Now you want to optimize that. You figure out, well, yeah, Postgres was great until, I don't know, like 100 million rows, 200 million, 500 million, whatever it is. But at some point, it gets slow-ish. So you try to figure out what is the option that we can actually do. So let's drop the table, because we're going to restart it. And we recreate it. And the table is super simple, right? It's a timestamp and value. But what we do now is that we actually have 3 tables where we say, please inherit from that table that we just created. So we're basically creating manual children, partitions, if you want to say that, right? And it's June, July, and August. Nothing fancy here. And now is where the magic happens. And that was true until quite a few years ago. I think until 2019 or something. Whenever Postgres became or got the feature declarative partitioning, until that point, you basically created a trigger and said, whenever you try to write to this like measurements table, please do something else instead. And that means our something else instead is basically when you find a date between June 1st and below July 1st, please write it to this first inherited table. If you find something between July and August, put it into the second. If you find something between August and September, put it into the third. Important, if you cannot find a valid range, please don't execute this at all, because otherwise it would actually go into the into the measurements table. So you would end up forgetting to create the new partitions, and you would wonder why this like parent table that is not supposed to have data is suddenly keep growing, right? And then you return null to say, yeah, whatever you originally wanted to do, forget that. So we create the trigger, and obviously we have to attach it. So we say, please put a trigger happening before insert. So before every single insert, execute that function that we just created. We throw in the data. Again, it's a little bit slower because triggers have overhead. Triggers are nice, but they have overhead. And if we execute the query again, we see 3 workers, a parallel sequential scan on, where is it? On the actual table. I can't see it right now. So 2, 3, I don't know. You have to believe me. I can't find it right now. So what it basically did is it looked at all of the 4 tables. 4 tables because we have a parent table which may actually contain data. because we forgot to block the insert, and free partitions. There's the third one. That is one that I was actually looking for. But what we didn't do is we didn't create indexes, so let's fix that. We can make it a little bit faster. But we still see that, and here is a little bit more obvious. We have the sequential scan on measurements, which is the parent table. As I said, it may actually contain something. We don't know. Obviously, it doesn't. And then we have index scans on those three tables. So that is how you did it in the past, right? And I said partition pruning, the possibility to say that data is actually, or that partitions are actually not being looked at, that doesn't happen here. That means if you have like 200, 400, 1,000 partitions, the query plan would actually contain every single partition. And believe me, the Postgres query plan, and I'm pretty sure that goes for all other databases as well, the higher the number of partitions, the higher the possibilities of finding the best execution plan. And finding the best execution plan has a lot of mutations, and it just keeps increasing. For Postgres, I think or from my own personal experience, it seems to be somewhere around like 100 to 120 tables when the query planner starts to go nuts. And you actually see query times greater than the extra execution time, like 20 seconds planning, 10 milliseconds execution. Not what you want. So that was that, right? And I said that had issues, and the Postgres people figured that it has issues. So they came up with a better idea. And the better idea was declarative partitioning. So bringing the idea of partitioning into Postgres and into the query planner and giving it the option to understand how this actually works. This time, the create table looks slightly different, right? Now we say we want to create this parent table, but please set it up to be partitioned by range. You remember, time series is the only thing you want to partition by range. And we actually tell it, here is your column for the range. So we do that, but we still have to set up the tables. This time, it is not a table that inherits from something. It's a partition of table. So they enhance the syntax of SQL to make that happen. And you actually give it actual values, so no trigger. All of that is handled by Postgres now, right? You create a partition which is in the range of June 1st and lower than July 1st. So we do that. We have June, July, and August. This time, because we already figured out we always want an index, we do that, and then we insert the data again. But the important thing is remember to create those partitions, because otherwise, Postgres will actually tell you, oh, I don't have a valid range for that, and all your inserts will fail. How that really works in reality or in a production environment really depends on your use case. When you put invoices into your database with like 30 days payment target, you want to make sure you always have the next month. If you have 90 days, you may want to make sure you have the next 3 months, right? So you always have to make sure you have enough tables to do that. And here is the cool thing or funny thing, and I never understood really why they did that. In Postgres, there is partition pruning, and you can shut this off. That's a brilliant idea, right? I just told you why the previous solution was bad, and now you wonder, why can you shut this off? And I wonder the same way, or the same thing. I do not know. So if I run this, what we see is there's a slight improvement. We only see 3 index scans. One over here, one over here, and one over here. So that means Postgres knows the parent table cannot include any data or cannot contain data, so we don't have to query it. If we have 1,000 tables or 1,000 partitions, that's not a great improvement. So let's switch this off. And to be honest, I think that is probably a debugging feature. I don't know. It's documented. It's in the document in a very prominent place. So you wonder why. But if I switch this off, and the date we're always asking for is July 14th to July 16th. So we're asking for 3 days of data, right? now we see what exactly happens and what we expect to happen, right? We understand we have 3 partitions with different time ranges, so why would I look into anything that cannot include this data? In a library or in a bookshop, the first thing you do is you look at the categories. Okay, so that's computer science. That's not what I'm interested in. I'm going for the manga, right? That's what we all do. You would not try to find a manga or something anywhere else in the bookshop except for that specific category. So that is how all of that happens, right? And that's great. It makes things easy. As I said, you always have to remember to set all up those partitions. So what can we do to make this a little bit better? And so far, everything is vanilla Postgres. Nothing special happening. No support at all from something else. And the folks at Timescale thought that must be easier. So you can do the partition automation with something like Partman, PG Partman, which is an extension you can use. But it has a really interesting way of doing stuff. Postgres has the option to set up a default partition, which collects everything that doesn't have a valid range. That's a weird concept, and it kind of reminds me of the parent table that does potentially contain data. The way Partman works is you write data, and eventually there's some cron job, and PG Partman goes ahead and says, oh, cool, there is some data in the default table. I may have to create a partition for that and move the data. Move the data basically means copying it over. The way Timescale works is slightly different. So let's do that. And we're back to the original create table. Timescale is older than declarative partitioning, so they never had the chance to actually use the syntax. So you set up the partition just as you would normally do. And then you have this magic function to turn this table into something Timescale calls a hypertable. It's basically the same thing. You have a parent table with some partitions underneath. Right, and you say, please take this table, measurements. Here's your index column. It's called TS. And because we want to stay in the same concept, please make that a chunk interval. You remember, a chunk is the same as a partition of 1 month. So we execute that, and nothing happens. It all looks the same, except for internally there was some magic being set up to say, hey, whenever something is being inserted, please do something else. And we don't have to set up partitions because that is the magic that now happens. So we're doing the same thing. We're inserting data. And if I run the exclude again, I can switch this off just because we don't care anyways. So if you do that, it does exactly what you want. So there's a few things we didn't do. We didn't set up partitions, and we did not set up an index. Because Timescale is built as a time series database. The only thing that makes sense is you have a time series or you have a timestamp column. Obviously, that thing wants to have an index, and obviously you need the partitions. So a lot of stuff that was done manually before has to be or is automatic now. And the interesting thing, and don't find the actual numbers. It should be faster. Don't take that numbers for granted. The previous version with declarative partitioning took about 10 milliseconds. The timescale version took about 4.3 milliseconds. It might be 10 and 5 or 10 and 7. Normally, timescale is slightly faster. But because we're a little bit nuts, and you may see where this is going, so let me do that and change that back. Right? So now imagine you're having around 90 days of data, and you want to set up all the partitions. 1 partition per day. In Timescale, you change this interval, and all the magic happens for you, right? So if I insert data now, it takes a little bit longer because it has to create more partitions. There we go. And if I execute it again, now we see that there's quite a few more partitions because now we're asking for 3 days of data, and we have more partitions we actually have to look at because we have 1 partition per day. So imagine what that would look like if I'd actually have to set it up in declarative partitioning. While I'm not working for Timescale anymore, the same sentence was true when I was working for Timescale. The beauty as developer advocate is, or as a developer relations person is, that you're not sales. You don't have to sell people, or you don't have to sell to people. What my intention is always showing people how easy stuff can be and why you want to use something, and then let them decide. That's why I showed how you can do all of that by your own, and I said there's PG Partman. I'm not a big fan of the implementation, but that may be different for other people, right? So far, you could do anything that we just did, and it would have just worked, right? Here's my table. It looks exactly like we expect, even though it's a hyper table now. It has internal partitions. It looks exactly like the database looked before. And I can show you those partitions. We have some magic schema. You see, I'm not that long gone from timescale. I'm still saying we. Timescale has this set of magic schemata that are not really hidden, but somewhat hidden. So anything like underscores timescale db underscore magic is something internal. It's either the catalog information to understand what chunks belong to what hypertable, or stuff like that. But that is basically where actual data lies. And I'm not sure if it's that hypertable. I'm just clicking it. I don't know. Now it's a different hypertable. Seems to be something with orders. But that is basically the partition where the data relies. And as a normal user, you don't have to know that, but it's fun to know. The important thing is it looks like a standard Postgres table. It behaves like a standard Postgres table. You don't have to do anything. But you do not have the overhead of the trigger, and you don't have to update the trigger, because that's something I forgot to tell you. When you look at that trigger, obviously, for every single new partition and every single new month, you would have to update that function. You would have to make sure that you update it in the same minute as the partition. So don't use that old concept, except for you're in on Postgres 10 or something. Don't do that. Upgrade and use declarative partitioning. But now that we have the data, we can do a few more things. And that is where timescale really becomes interesting, because they have quite a few options on top of that. So what I can do is I can say, I want to enable, and if it does not see the right instance, that one. Yeah, take that one. I can enable compression. Compression is exactly what it sounds like. It will try to compress the information. And I would have to understand what hypertable I have to change now. Let me see. Measurements, it's 144. So let's take something like 144. Yeah, whatever. Let's take that one. So now I manually compressed that chunk into a smaller representation. What timescale does internally is basically creating a columnar-like storage, saying, OK, all of the same columns go into a specific columnar entry and being compressed together. Obviously, you can set that up with a policy and say, hey, please compress everything older than a month or so, or older than 2 months. And the compression, and I unfortunately don't have access to my previous timescale cloud instance, which had an incredible example. The compression works on a data type level. That means there's data type specific compression, which goes up to like 10x. So basically bringing down 1 terabyte to 100 gigs, to 10 gigs. And even further, depending on what you do. So that is one thing, and let's make sure that those are not existing. I think they're not. So then timescale has one other feature, and I think this is really incredible, and it was one of the most commonly used features. With time series, when you store data, you normally want to analyze it afterwards. You can run all those analytical queries on the fly, or you can pre-process or pre-calculate some of the values. Right? Some people do this with stream processing. Timescale has, well, a materialized view, which is incrementally updated. Materialized views is known? OK, there's some people not. So a materialized view basically is you do some calculation, where you define a query, the query does some calculation, and the result of the query is being stored to disk. It's basically materialized as a result set, which means you have to refresh it because it doesn't refresh automatically. And refreshes in Postgres materialized views are always all or nothing. So you throw away all your stuff you had before, and you recalculate it and store it again. The idea is that if you have that result set on the disk, you can actually query it in the speed of a standard Postgres table. So Postgres Timescale took this idea and said, hey, let's make it, and I'm not a big fan of this name, it's called a continuous aggregate. So a continuous aggregate is an incrementally updated materialized view. So it's not all or nothing. It basically updates itself automatically with a policy over time. So the continuous aggregate understands, OK, that was the last timestamp I calculated, so everything after that needs to be recalculated and added. But from a perspective of the user, it looks exactly like what you would expect. So in this case, I said, I want 15-minute chunks or time buckets. So aggregate in 15-minute buckets and do an average. And because I do want to do some aggregation on top of aggregations, I may need the sum and the count. We all know average on average is not a great idea, except for very specific cases. So it looks exactly like the standard stuff. And if I add one more row, let's quickly do it. 4 minutes left. That's perfect. Let's see. So that should be the first row. Let's make it, I don't know, 14.99 and store it. I said store it. There you go. And if I refresh that, it should update. Imagine it updated. Live demos. Everything went smooth until now. Something had to happen. Oh, I know. I know. I updated an old range. That was stupid. Let's try that again with something more meaningful. Let's say we're going for the 1st of September and do that and save it again. And that value certainly didn't exist before, so we should be able to see, there you go, September 1st, 14. So if you update old ranges, it will only recalculate those if you actually ask it for it. The main reason behind that is you could actually remove the original data, the raw information, for disk space reasons, and the continuous aggregate would still keep the aggregated result, which is really nice if you have something like IoT data, which comes in like 100 milliseconds or a second granularity, but you know I need a minute granularity anyway. So you can do like an initial roll-up and then store the results. Right, 3 minutes. So where to go next? Those are still all blog posts on timescale.com, and they're really blog posts. Interesting. All right. I love the live caption. So what is time series data is a blog post that one of my colleagues wrote, also previous colleague. It's a little bit deeper into the idea of like how do you actually define time series? What does it mean? How do they work internally? And how do you realize, OK, that data set is a time series? Another one, which is slightly older, we had an amazing colleague, and she was all into NFL. NFL fans here? All right, yeah. It works better out in the States. In the States, you have a lot more hands. And the other ones would say NHL, but it's close enough. But the interesting thing about a lot of the US sport organizations, they give you an amazing data set. And what she did was analyze the heck out of that. It's a really interesting blog post to read it and to see how you would actually go ahead and optimize stuff on a play field, right, based on the capabilities of people. And the last one, when you stored all the time series information, you want to analyze it, but you also want to do forecasting. And forecasting is a really important thing, right? If you know how users behave, you remember the Netflix thing, you actually want to understand how we can make that into the future. So that's the third one, and it's really beautiful. And we have 1 minute left. Man, I did a good job. Questions? Yes?
Under which circumstances would you replace something like Influx or Prometheus or whatever with this?
Under what circumstances would you replace something like Influx with timescale.db? I think it really depends on scalability. Influx, everyone who used Influx at some point knows that there is some scalability limitation. One of the things that I normally say is storage reliability. I think Influx is around for long enough that this is not a valid thing. Everyone who's on QuestDB, I think Jaromir isn't here, so he can't hit me. Remember, QuestDB is fairly new. People say you need about 10 years to get a storage engine stable. But for that, when you hit scalability issues, before that, I think there is not really a valid use case to change stuff. Or the other thing is when you want to have a different data model. Influx has a very specific, very strict data model. If you want to have a more free, more relational kind of data model, especially when you have to join external data, that is probably where you want to look at that. We're out of time, but nobody's going to throw me out because I'm the last one, so feel free to keep asking. Otherwise, thank you very much. I know you all want to go for the beer. I'm sorry.